just give you this hint here because I have papers here. You are going to be doing some Taylor series analysis later on. But here, this is a demonstration of how to do it for forward Euler. Okay. Let me just complete how to do the analysis to forward Euler, and probably that's going to give you a good sense. So for forward Euler, because when I write down the Taylor series expansion, I can see that the first term gets cancelled, the second term becomes what we want, and we only need one additional term. So what I'm going to write is ut plus delta t is going to be, of course, I need the first term, otherwise I won't be able to cancel. Of course, I need the second term, the linear term, otherwise I won't get what I need to get. And I'm just going to carry one additional term. And what do I do with the rest of the terms? I'm going to write the rest of terms using what I call a big O notation. Write a big O here and put delta t to the cube here. This big O notation means everything proportional to delta t cube or proportional to some higher order polynomial of delta t cube, right? So anything that is a delta t cube times something plus delta t to the fourth times something plus delta t to the fifth times something can all be lumped into this, right? So it's basically all the polynomial terms of delta t starting from delta t cubed, right? Okay, so once I do that, the Taylor series expansion becomes easy and I can analyze the error, right? The error, again, is the difference between what I want to approximate and what I use to approximate it. So this is what I want to approximate. And then I plug in the Taylor series. So the first term becomes ut plus du dt times delta t plus half of d square u dt square delta t square plus this big O notation. That's going to be something, I'm just saying something I don't care. Okay, so this is this guy. Okay, and minus ut divided by delta t. Okay, so now I can see that, so first of all, let's cancel stuff. This gets cancelled with this, right? And this delta t gets cancelled with this, right? And if I cancel delta t, the square is going to cancel out, and the cube is going to become 2, right? This is going to be something you'll be doing a lot. If I have a big O notation, if it's big O delta t cubed, that means all the polynomials delta t to the cube and higher. If I divide the entire polynomial by delta t, what do I get? I get polynomial terms proportional to delta t square and higher. So if I divide O delta t cubed by delta t, I get O delta t squared, right? Okay, so now I then also have this guy get cancelled with this, right? So what I get is half of d square u dt square times delta t plus O delta t squared. So this is what I get. I mean, this is how much error I get in forward Euler.
Shouldn't that be negative, or are you just taking the absolute value?
Oh, yeah. I should be negative. Thank you. Yeah. All right. So, what does that tell us? It actually tells us that if delta t in our previous case is equal to pi over n, right? Then my e actually goes proportional to 1 over n, right? I mean, this means proportional, some constant times 1 over n. This is exactly what we are observing here, right? As I increase n by a factor of 10, the error decreases by a factor of 10. So the mathematical analysis using Taylor series expansion actually explains the behavior of forward Euler. And this also tells us that, I mean, there is nothing in the analysis that has to do with what equation I'm solving, right? I'm only dealing with the approximation to the time derivative. The time derivative can be a term in any equation, as long as I'm not approximating anything else in the equation. This is the error I get, right? It means no matter what equation I'm solving, I expect this behavior out of forward Euler, right? I mean, it generalizes this experimental trend to any equations.